The mountain looks almost too perfect to be dangerous. Rising above the forests of the Pacific Northwest like a white stone monument, Mount Hood carries the classic shape people imagine when they think about volcanoes. A steep cone, a snow-covered summit, glaciers draped across dark volcanic rock. It appears orderly, balanced, almost frozen in time. Yet beneath that calm profile sits one of the strangest volcanic systems in the Cascade Range, a volcano that repeatedly refuses to follow the behavior scientists expect from a large stratovolcano. Why does it erupt differently from nearby volcanoes? Why does it produce thick lava domes instead of massive explosive caldera forming eruptions? Why does it generate dangerous debris flows even during periods without major eruptions? And why does its magma seem to stall, cool, and reorganize inside the crust instead of rising quickly toward the surface like it does beneath more predictable volcanic systems? Mount Hood is often overshadowed by more famous neighbors such as Mount St. Helens and Mount Rainier, volcanoes known for catastrophic explosive behavior. But for geologists, Mount Hood may actually be the more puzzling mountain. It does not behave like a normal Cascade volcano because the entire plumbing system beneath it operates in an unstable middle state between dormancy and activity. The volcano repeatedly builds magma reservoirs that never fully mature into large eruptible chambers. Instead of storing huge volumes of molten rock, Mount Hood appears to maintain small, isolated pockets of magma that cool rapidly, crystallize heavily, and evolve chemically before eruption. This creates a volcanic system dominated by sticky lava, unstable domes, collapses, and prolonged low-level unrest rather than giant explosive blasts. The mountain exists because of the same tectonic engine that drives the entire Cascade volcanic arc. Off the western coast of North America, the small oceanic Juan de Fuca plate dives beneath the North American plate in a subduction zone extending from Northern California into British Columbia. As the dense oceanic crust descends into the mantle, water trapped within hydrated minerals is released under increasing temperature and pressure. That water enters the overlying mantle wedge and lowers the melting temperature of mantle rock. Partial melting begins, producing buoyant magma that rises upward through the crust. This process feeds the Cascade volcanoes. At first glance, Mount Hood should behave similarly to other volcanoes in the arc. The tectonic setting is not unique. The source of magma is not unusual, yet the mountain produces eruptions that differ significantly from many neighboring systems. One major reason lies in the composition and temperature of its magma. Mount Hood commonly erupts andesite and dacite, intermediate magmas that contain relatively high silica content. Silica increases viscosity, making magma thicker and less fluid. But viscosity alone does not explain Mount Hood's unusual behavior. Many Cascade volcanoes erupt silica-rich magma. What makes Mount Hood distinctive is the way its magma evolves before eruption. Deep beneath the volcano, magma generated in the mantle does not simply rise directly to the surface. Instead, it enters the crust where it stalls repeatedly in temporary storage zones. These reservoirs are not large molten oceans. Geological evidence suggests they are more like crystal-rich slurries, partially solidified regions where magma exists in fragmented pockets surrounded by solid rock. Over time, cooling causes minerals to crystallize out of the melt. As crystals form, the remaining liquid becomes even more silica-rich and viscous. This process changes the physical behavior of the magma dramatically. A hotter basaltic magma may flow like syrup, but Mount Hood's evolved magma behaves more like thick cement. Gas bubbles have difficulty escaping through such viscous material. Pressure builds slowly. Yet paradoxically, Mount Hood often does not produce the giant explosive eruptions associated with gas-rich viscous magma systems. The reason involves the size and connectivity of its magma reservoirs. Evidence from mineral chemistry shows that Mount Hood's magma storage zones are relatively small and transient compared to the enormous long-lived chambers beneath highly explosive volcanoes. Crystals within erupted rocks preserve chemical records of temperature and pressure changes inside the crust. Many Mount Hood minerals reveal repeated cycles of heating, cooling, and magma recharge. This indicates the system is constantly being disturbed by injections of new magma from below, but those injections rarely accumulate into a massive unified chamber. Instead, the system behaves like a fractured network of magma pockets that partially solidify between eruptive episodes. When fresh hot magma intrudes into these crystal-rich zones, it can remobilize portions of semi-solid magma, generating eruptions without requiring the formation of a giant molten reservoir. This creates a volcano capable of erupting repeatedly while still appearing dormant for long periods. That unstable storage mechanism may explain why Mount Hood's eruptions are often dome-building events rather than highly explosive caldera eruptions. Thick, viscous lava struggles to travel far from the vent. Instead, it piles directly above the eruption point, forming lava domes. These domes are inherently unstable because the lava cools and fractures as it accumulates. Internal gas pressure, gravitational instability, and continued magma intrusion can cause sections of the dome to collapse. When a lava dome collapses, it can generate pyroclastic flows, extremely dangerous avalanches of hot ash, gas, and rock fragments moving at highway speeds. Mount Hood has produced many such events throughout its history. One of the most significant eruptive periods occurred roughly 500 years ago during the Old Maid eruption sequence. During this period, lava domes formed near the summit and repeatedly collapsed, generating pyroclastic flows and lahars that swept down river valleys. The lahars are especially important because they reveal another reason Mount Hood behaves differently from many volcanoes. The mountain supports extensive glaciers despite its volcanic heat. Snow and ice cover large portions of the summit region. When eruptions occur, hot volcanic material rapidly melts snow and glacier ice, producing enormous volumes of water mixed with ash and rock debris. These mixtures become volcanic mud flows known as lahars. Lahars are among the deadliest volcanic hazards because they behave like flowing concrete. They can travel dozens of miles downstream while carrying huge boulders, uprooted forests, and volcanic sediment. At Mount Hood, lahars have repeatedly transformed river systems. During the Old Maid eruptive period, lahars filled valleys, blocked rivers, and destroyed forests across large regions surrounding the volcano. Yet Mount Hood's lahars are unusual because they are not always directly tied to major explosive eruptions. The volcano's steep slopes, unstable hydrothermally altered rock, and glacier-covered summit create conditions where landslides and debris flows can occur even during periods of low eruptive activity. Hydrothermal systems circulating acidic fluids through the volcano weaken rock over time. Minerals are chemically altered into soft clay-rich material with low structural strength. Entire sections of the volcano become mechanically unstable. This process fundamentally changes how the mountain evolves. Instead of growing steadily through lava accumulation, Mount Hood constantly destroys itself through collapse and erosion. Ice carves deep valleys into volcanic rock. Hydrothermal alteration weakens the summit core. Gravity pulls unstable slopes downward. Repeated collapses reshape the mountain faster than many people realize. Scientists studying Mount Hood have discovered that its summit region contains heavily altered rock, weakened by long-term interaction with acidic fluids and volcanic gases. These hydrothermal systems operate like underground chemical reactors. Hot water dissolves minerals, transports metals, and alters solid volcanic rock into weaker materials. Over thousands of years, this creates zones highly vulnerable to structural failure. That means Mount Hood's greatest hazard may not necessarily come from a giant explosive eruption. Instead, moderate eruptions interacting with ice and unstable rock can produce devastating debris avalanches and lahars. This makes the volcano dangerous in a different way from the classic explosive image associated with volcanoes like Mount St. Helens. Another factor that separates Mount Hood from more typical volcanic systems is the timescale of magma storage. Studies of crystal diffusion suggest some magma beneath the volcano may reside in the crust for centuries or even millennia before eruption. Crystals record chemical zoning patterns created when conditions inside magma chambers change. By measuring how quickly elements diffuse across crystal boundaries, scientists can estimate how long magma remains stored before eruption. At Mount Hood, these timescales reveal a sluggish volcanic system. Magma often cools extensively before erupting. In many cases, eruptions appear triggered by new basaltic injections reheating old crystal-rich magma rather than by direct descent of fresh mantle melt. This recharge process is critical because it creates instability inside partially solidified reservoirs. Imagine a thick, crystal-rich mush sitting deep underground at temperatures barely above solidification. Then imagine hotter magma suddenly injected beneath it. Heat transfers upward. Volatile gases enter the system. Crystals partially remelt. Pressure increases. The result is not a smooth, stable magma chamber, but a mechanically chaotic mixture of solids, melt, and gas. This explains why Mount Hood sometimes displays prolonged seismic unrest without immediately erupting. Earthquakes beneath volcanoes often indicate magma movement, fluid migration, or fracturing rock. At Mount Hood, seismic activity may reflect small magma intrusions interacting with partially solidified crustal storage zones. Yet those intrusions do not always produce eruptions because the magma can stall, crystallize, or dissipate heat before reaching the surface. In essence, Mount Hood behaves less like a continuously molten volcano and more like a periodically reactivated crystal mush system. This is a major shift in how volcanologists now understand many volcanic arcs worldwide. For decades, magma chambers were imagined as giant underground lakes of liquid rock. Modern research increasingly shows that many volcanic systems spend most of their existence in semi-solid states. Mount Hood appears to be an especially strong example of this behavior. Its eruptive style also reflects the role of regional tectonics beyond simple subduction. The crust beneath the Pacific Northwest contains numerous faults and inherited structural weaknesses created through millions of years of tectonic deformation. These structures influence where magma rises and where it stalls. Mount Hood's magma pathways appear strongly controlled by crustal architecture. Seismic imaging suggests magma may migrate through narrow, vertically oriented conduits rather than accumulating in one enormous chamber. This fragmented plumbing system helps explain the volcano's inconsistent behavior. Some eruptions originate near the summit, others emerge from flank vents. Magma may ascend rapidly during one eruptive episode and remain trapped during another. The chemistry of Mount Hood's lavas further reveals a highly dynamic system. Mineral assemblages show evidence of magma mixing, where hotter basaltic magma intrudes into cooler evolved magma reservoirs. This interaction produces complex thermal and chemical gradients inside the volcanic system. Crystals formed under one set of conditions may later be transported into entirely different magmatic environments. For example, plagioclase crystals erupted at Mount Hood often display zoning patterns indicating repeated cycles of heating and cooling. Some crystals contain resorption textures where previously formed mineral surfaces partially dissolved after exposure to hotter magma. Others preserve abrupt chemical boundaries showing rapid environmental changes within the magma reservoir. These mineral records demonstrate that Mount Hood's plumbing system is highly unstable and repeatedly reorganized. The volcano is not supplied by a single simple magma source. Instead, multiple magma batches with different temperatures, viscosities, and gas contents interact beneath the mountain over time. Gas behavior is another critical factor in the volcano's unusual nature. In many explosive eruptions, dissolved volatiles such as water vapor and carbon dioxide separate rapidly from magma as pressure decreases during ascent. Expanding gas bubbles drive fragmentation, producing explosive ash columns. At Mount Hood, however, high crystal content may alter how gases move through magma. Crystals can either trap gas or create pathways for degassing, depending on their abundance and arrangement. Some studies suggest Mount Hood's magma may partially degas before eruption, reducing explosive potential while increasing viscosity even further. This combination leads to eruptions dominated by thick lava extrusion instead of sustained Plinian explosions. Lava emerges slowly, accumulating into domes and stubby flows, rather than producing towering eruption columns. Yet this does not make the volcano safe. Dome collapses can occur suddenly and generate highly destructive pyroclastic density currents. The glaciers covering Mount Hood add another layer of complexity. Ice-volcano interaction fundamentally changes eruptive dynamics. When magma encounters ice or meltwater, rapid steam generation can fragment magma violently through phreatomagmatic processes. Water flashing instantly into steam expands explosively, shattering surrounding rock and magma. Even relatively small eruptions can therefore become disproportionately hazardous in glacier-covered environments. Meltwater channels rapidly concentrate debris into river valleys, directing lahars toward populated regions. Mount Hood's river systems effectively act as hazard corridors, extending volcanic risk far beyond the summit area. The volcano's glaciers themselves are also unusual because they are heavily influenced by geothermal heat flow. Areas near fumaroles and hot ground experience accelerated melting. Ice caves form where volcanic heat melts tunnels beneath glaciers. These systems provide evidence of persistent subsurface heat even during non-eruptive periods. That persistent heat indicates the volcanic system remains active despite long quiet intervals. Mount Hood is not extinct. It is a living volcanic system maintained by ongoing magma supply from subduction-related processes deep below the crust. Yet predicting its future behavior remains extremely difficult, precisely because the volcano does not follow simple eruptive patterns. Large explosive eruptions are possible, but smaller dome-building episodes may be more likely. Significant hazards could develop even without a major eruption through sector collapse, debris avalanches, or lahars triggered by hydrothermal weakening. This uncertainty challenges volcanic hazard assessment. Many volcanoes exhibit relatively consistent eruptive behavior over time. Mount Hood instead occupies a gray zone between explosive stratovolcano behavior and slow dome-building volcanism. Its geological history contains both explosive activity and long periods dominated by lava extrusion and collapse. Modern monitoring efforts focus heavily on seismic activity, ground deformation, gas emissions, and thermal anomalies. But interpreting those signals at Mount Hood is particularly challenging because the magma system appears fragmented and episodic. Small intrusions may create unrest without eruption. Hydrothermal fluid movement can generate seismic signals resembling magma migration. Glacier dynamics may interact with volcanic heat in ways that complicate surface observations. Even the shape of the volcano reflects its unusual internal behavior. The steep summit region results partly from accumulation of viscous lava near eruption vents. Fluid basaltic volcanoes typically form broad shield-like profiles because lava flows travel long distances. Mount Hood's sticky magma instead piles vertically, creating steep, unstable slopes vulnerable to collapse. Over time, glaciers carve those slopes aggressively. Freeze-thaw weathering fractures volcanic rock. Water infiltrates cracks, freezes, expands, and mechanically breaks apart the mountain. This interaction between volcanism and alpine erosion continuously remodels the volcano. In many ways, Mount Hood is less a stable mountain than an active geological battlefield between magma construction and erosional destruction. Lava builds upward, ice cuts downward, hydrothermal fluids weaken the core, gravity tears unstable sections apart. Every visible feature on the volcano reflects this ongoing competition. Its future evolution will likely continue following this pattern. Fresh magma from the mantle will rise beneath the Cascades as long as subduction continues offshore. Some of that magma will infiltrate Mount Hood's crustal storage zones. Much of it may cool and crystallize underground. Occasionally, portions will remobilize and erupt. When that happens, the volcano will probably not behave like the stereotypical image many people expect. It may not produce immediate catastrophic explosions visible around the world. Instead, it could enter prolonged periods of dome growth, collapse, glacier melting, and lahar generation. Hazards may unfold over weeks or months rather than hours. That slow building instability is precisely what makes Mount Hood scientifically fascinating. The volcano exposes a deeper truth about volcanic systems. Many are not simple molten chambers waiting to explode. They are evolving crustal machines shaped by heat transfer, crystal growth, tectonic stress, volatile migration, hydrothermal alteration, and mechanical collapse, operating simultaneously across vastly different timescales. Mount Hood stands as one of the clearest examples of that complexity. Beneath its calm, snow-covered summit lies a volcanic system constantly balancing between solid and liquid states, between eruption and dormancy, between construction and collapse. It does not behave like a normal volcano because the processes driving it are not stable, orderly, or fully connected. The mountain exists in transition, a volcano perpetually reorganizing itself from the inside out. And that may be the most important lesson Mount Hood offers geologists. Volcanoes are not static structures with predictable personalities. They are dynamic systems controlled by countless interacting variables hidden deep underground. Mount Hood simply reveals those complexities more openly than most. Beneath its beautiful symmetrical profile is a restless geological engine that refuses to settle into a single eruptive identity, a volcano whose greatest mystery is not whether it will erupt again, but why it behaves so differently every time it does.